So welcome back, Earth scientist. Hopefully you've taken some time to research Yosemite National Park and how it formed. This is actually going to be an important question for or questions, I might add, for your test. So I think you should go look it up if you didn't take that time. I'm going to give you a little bit of the history to get you enticed enough to want to do some of your own research. And some of the best places to get your research on geologic histories of national parks is to go to the National Park System main web page and type in whatever national park you're wanting to look at, or national forest. In the case of Yosemite, the story starts a long, long time ago during the Mesozoic era, that's dinosaur time frame, where we had an island arc approaching the west coast of continental North America craton. And what happened was when that island arc smashed into us, it was part of an oceanic plate. As you learned earlier in some of our other lectures, ocean plates sink beneath continental plates. When this occurred, it created a fault line between the continent and this land that accreted on. At some point, the land on the continental side broke free from this particular from the fault zone and uplifted. Well, that's just part of the story. Once you get uplift, rocks are subject and prone to weathering and erosion. And that happened over a series of multiple millions of years with new deposition on top. Then the last ice age comes into play, and massive valley glaciers existed in this area. You have to imagine that the largest mountain in this region of the Sierra Nevadas is Mount Whitney, sitting about 14,000 feet above sea level. So when you understand that there's a series of these large structures, Yosemite is just one piece of the puzzle of the Sierra Nevada range. And even then, there's a much more extensive history about why does Yosemite not have a typical U-shaped profile from glaciation. So the point of all this is that you start looking at landscapes and realizing that there's a chronological sequence of events that occur. And you may need more information to interpret what you're looking at. One way scientists do that is through mapping. Mapping is important so we can actually bring a bigger picture into a small representation that we can actually interpret. That's also the philosophy of geographical information systems, known as GIS mapping. You want to put things into an interpretation that you can analyze and extrapolate the correct information from to make good quality decisions, conclusions, and hypotheses. So essentially, maps allow us to look at landscapes in manageable shapes and sizes, because we can't be looking at the Sierra Nevadas simply by driving it or flying over it only. While both of those can be very useful tools, especially the aerial flyover, it doesn't give us the scope down at the ground how important each and every square foot is. So what we will do is we'll make map projections. These are used to make maps of the Earth, and they are essentially points that are transferred and the lines of the Earth to paper. So we can take a pinpoint location like Yosemite and plot it onto a map. There's multiple different ways to make map projection, and each map is slightly distorted in some shape, fashion, or manner simply because of how the map is made. So in a global view, we're trying to look at latitude. First of all, latitude are like the equator lines, even though they're imaginary. So one way we look at maps is through a global view for longitude, which are the meridians that run from pole to pole. So essentially, instead of being equators that are parallel and running this direction around the perimeter of the Earth, we're looking at pole to pole, making a circumference of the entire Earth. The center longitude is called the Greenwich Meridian, and then there is a special meridian that's called the International Date Line, and that is at 180 degrees around the world from the prime meridian. So I've crossed over the International Date Line, and if let's say you're going to Australia and New Zealand, you would cross over the international date line coming from North America. And let's say you left on a Wednesday, you would be on a plane for about 17 to 20 hours, and you would end up on Friday in Australia, New Zealand, and it's still Thursday in North America. It almost makes your brain hurt. And when you come home, subsequently, you'd be going back in time. So when you cross that international date line, that's in a significant location for travel purposes around the globe. So time zones are measured by the Earth's movement in relationship to the sun. And for a test-related question, there are actually 24 time zones on Earth because it takes the Earth 24 hours to make one full rotation around the sun. And so we have 6 of those 24 right here in the United States. And you are currently residing in this one right here, known as Central Time. So Eastern Time is 1 hour off from where we are. This is Mountain Time, and then Pacific Time. Where it gets a little crazy is there's a couple of states that do not recognize daylight savings time. For extra credit, I'm giving you the opportunity to submit a paper up to Blackboard, and I'm not asking it to be more than 1 or 2 pages long, as long as it's accurate and thorough and properly cited. Tell me which 2 states do not recognize daylight savings. That's question 1. And include my question so I know that you understand what I ask. Then put your answer. Once you put your answer, skip a line or 2 and go to question number 2. What is the environmental benefit for having daylight savings time? There's actually an environmental benefit, and I hope that you can find that out. The third thing I want you to research is what specific president passed this into law, and when did that occur? Which famous person actually proposed the idea of daylight savings time, and why? So those 4 things can be 5 points for your next test if properly answered. So you submit this by midnight to the Blackboard Message Center on the date noted in the announcement that I have for this particular extra credit assignment. Have fun with this. It's actually enjoyable. One of the states is even more confusing, and I want you to find out. I guess question 5, I'm going to add one more question. Why does this one state not recognize daylight savings time? There's something special about it, because part of the state kind of does, part of it does not. All right, on a global view, the Earth is divided into 60 UTM zones. That's universal transverse Mercator projections. And each of these represents 6 degrees of longitude wide. So problems can arise when you're matching adjacent maps which lie in different UTM zones. And so you have to know which map comes next, and you can find that on the edges of your maps because it'll tell you which map to refer to. So here's what UTM zone numbers look like, and the entire Earth is gridded out into this fairly predictable complex system. But what I want to point out is, do you see that there's some distortion way up here? So depending on what kind of map you're looking at, there can be distortion in different parts of the map, simply based on how the map is designed and what kind of information the map is giving us. Mercator projection. These have correct shapes of the continents, but continents do have a distorted area. So you can kind of see in looking at this map that some of the continents don't look like they're full 100% good shape. Longitude lines are parallel, but the latitude lines are somewhat distorted. You can really see that in this area right in here, and that in between the 30 and 60 degrees north and south latitude, and certainly from 60 degrees up to 90. So obviously the areas around the poles are more exaggerated. We're trying to give more specific accuracy to the middle section of the world. Conic projections are typically used to help plot weather and road maps, and they are typically done with smaller geographic locations as opposed to worldwide size maps. they project a specific location from the globe and kind of focus in, zoom in on that area. Topographic maps are some of the most useful tools, especially to an Earth scientist, because this shows changes in elevation of the Earth's surface. So we can actually look at a three-dimensional picture, even if it's not a relief map. The way we can look at three dimensions is by simply interpreting lines that have been drawn on the map that are called contour lines. Contour lines represent an elevation at the same level. So let's see, you have an elevation line of 10,000 feet. That entire line that's drawn, let's say around a mountain, that would be 10,000 feet. Let's say we had a contour interval of 1,000 feet. So the next line up would be 21,000. The line above that would be 22,000. Typically a contour is much smaller than 1,000 feet in elevation. And in our area, most contours are around 10 to 50 feet. If you get up into the mountains, that could be 500 feet or 100 feet. It just really depends on where you are. But that's one of the first things you look at in a legend of a map, is to determine what the contour interval is. Every fifth contour line is darkened on a map to make it easier to visually interpret, and those are called contour index. That would look like something like these lines right here. And if you start seeing how this one's darker, this one's darker, this one's darker, that is an example of an index contour. And so that just helps you know where you are. And usually on most index contours, there'll be a number so you can interpret where you are in either going up and down in elevation. So when we're asking you to find the highest elevation point, usually it's not X marks the spot. When you're looking at the topographic map, you're trying to figure the tallest contour location. So in this particular map, you would have to look at the contours, and I'm going to tell you, the closer the contours are together, the steeper the topography. The further apart it is, the flatter it is. So take a moment to look at this topographic map and interpret which areas would be have the most steep and vertical type elevation, and which specific parts of the map would be more flat. I think that's important enough to know for a test. So I could easily put an interpretation question up of a topographic map. So let me do this with you. Notice how close together these contours are. They actually fold. So this is a highly folded rock, by the way, which is indicative of mountain building. So all these really close contours would mean you'd have a very large hill or mountain. And I can tell you from this area, it's a mountain. But notice these areas are much flatter. Maybe they're the tops of mountains. We would need to look at the contour interval number to determine if it's the top or if it's at the valley at the bottom. But notice that the farther the spread apart is, that means that there's not, the contours don't change as dramatically as fast. So when you're looking at the contour interval of a map, that's one of the first things you have to look for, are trends that you're seeing. Remember, the purpose of a map is to make assessments, conclusions, extrapolate information to interpret what the map is trying to show. So these index contours mark specific elevation points. And what I mean by that is, let's say that line is 5,000 feet, and then the contour interval is 100 feet. So the next one would be 5,100, 52, 53, 54. At 5,500, I would have my index contour. So read the elevation numbers to determine if the structure is either a hill, a basin, a dome. And you're going to look for hatchers. And hatchers are little, if you have a line drawn like this and you have a little point that comes down, that represents the dip, DIP, which is the elevation or grade from its original position. And these short lines at right angles to the contour line depict if whether you have a depression or you have a some kind of a hill. Usually it points inward. If you have a circle that has little hatcher marks that come all the way in, that represents going down in elevation or dip, and that would be a basin. Why would that be important to you if you're mountaineering or if you're hiking? You may need to have rappelling gear, you may need to have climbing gear based on looking at a topographic map, or both. So when you're planning trips, you need to consider looking at a topographic map for your area. They're available through United States Geological Survey, known as USGS, and you can order them by quadrangle, and a quadrangle is usually 7.5 minutes of the Earth's section of minutes and hours, like we were talking about, that it rotates around a 24-hour. It covers 7.5 minutes of the planet. So when you're looking at maps, another way to do it, some maps are total relief, and that means they actually have, you can touch it and there's relief, three-dimensional relief. That's very valuable as well, and most of them also have contour lines to help you interpret what you're looking at. So I can just kind of look at this one right here. First of all, do you see the hole up here? And this is Mount Ranier. I went there this summer, and I can tell you that this is a highly glaciated mountain, and I can see evidence of that. I want to point out these broad valleys right in here. This one's a river valley, but see how broad this one is right here and how U-shaped profiles these are coming down. That's very indicative of valley glaciers. This up here is the summit, and this is where if an eruption happened, it would happen out of this section. So we can look at the contours, and if you were planning a hike to Mount Rainier, you would need to know a lot about how tall the elevation is, because when you get up to this point way up here, there's the last National Park System headquarters there, absolutely stunningly beautiful. It gets pretty dangerous when you're hiking. Enough for there to be a welcome crew for every hiker that makes it down the mountain. That should give you an understanding, and they dong a bell and wish you well when you come back, because sometimes hikers don't make it back, and it's because they're not prepared for the terrain, or they're not in the right shape. Remember that contour lines can never cross one another. If they do, it would mean that they didn't represent that specific elevation, and they would have two different elevations. Since that's important for a spot to have two elevations of different numbers, contours by definition must have one elevation. Contour lines that form V's, they point the upstream whenever they cross streams. Because streams flow in depressions that are lower than the surrounding areas, you can use contour shapes to help interpret what kind of landforms might be there. So that could be valuable to you in hiking in terms of how many rivers am I going to have to cross? Do I need to research how deep these rivers are before I go? And the flow and velocity, because it may not be manageable to cross by foot. You always need to look at the legend and the scale. So the legend explains any symbols that might be used on the map. It also gives you the contour interval, but the scale is really important. For example, if I have a 1 to 24,000 series map, that means that 1 inch on the map equals 24,000 inches on the ground. That would be a great test question. So if I'm looking at a map that's 1 to 150,000, that would mean that 1 inch on the map equals 150,000 inches on the ground. So let's use an even bigger one. Let's say I'm using a 250,000, 1 to 250,000. That means one little bitty inch on your map equals 250,000 inches on the ground. So my question to you is the 250,000, 150,000, or 25,000 going to be a more detailed map? And you need to think about it for a second. So once you ponder that, I'm going to come back to that concept shortly and let you know what the answer was. So the type of map that you select directly needs to be correlated to the information that you need to be using it for. Do you need a Mercator map? Do you need a conic map? Do you need a topographic map? Sometimes you may need a combination of maps. Not all maps are the perfect fit for what you're wanting to do, but each serve their own unique purpose in interpreting data to make quality decisions. Now, how do we map our planet? Since it's so huge, we need to do a lot of it from outer space. Remote sensing uses satellites in order to help us map out the shapes, topography, and so forth of the planet. So what we can do is detect several wavelengths of energy emitted from the Earth's surface, typically as reflective from the sun, and it can show landforms in extreme detail, helping us put together a very accurate remote sensing map of our planet. We can use several specific satellites that use radar to compute the distance to the ocean's surface, and then also use in that technology to map the bottom of the ocean floor. Even this week that I'm filming this particular video, about a week ago, about 1,000 new seamounts were discovered at the bottom of the ocean floor using this technology. So we still have lots to learn about our planet and mapping out our planet. One key way that we make maps is by global positioning system. I mentioned GIS earlier. GPS is actually used to determine an exact, precise latitude and longitude location on Earth. We use it for tracking hiking, for wildlife. We can even use it for plate movement. So if I put a series of GPS stations, plot them all over plates that are moving, and I know their origin point the day that I put that GPS monitor in place, I can see what direction the plate is traveling and how fast it may be traveling. So we can also use remote sensing underwater, and we do this to bounce sound waves off of the bottom of the ocean floor to help make sonar maps that give us relief at the bottom of the ocean floor. This is how we discovered the deep sea trenches like the Marianas Trench, how we discovered there's a gigantic series of mountain ranges at the bottom of the ocean called mid-oceanic ridges. That's how we've discovered all these brand new seamounts I discussed. So this was important information. One way it is because it helps us identify potential locations for economic resources, especially along the continental shelf and continental slope. Here's an example of sonar testing. We'll use equipment like this and then map out the bottom of the ocean floor where we may not be able to easily get down there. You're like, oh, we could just send a submersible. Okay. At $25,000 to $40,000 a day, that's pretty steep. And not many people are going to have the grant funds to go down there and just do that. So there's an easier, more cost-effective way to get the job done with higher accuracy. So I'm going to have a quick review with you. What kind of landform is this? Do you remember what it was from our first part 1? And how it was made. That'll be a test question. First of all, this is Bryce Canyon National Park in Utah. That's one part you need to know. And remember, I talked about these fins right here, how they were made. See if you can think about how that was made. You may need to go back to the video and watch. Before I go on, do y'all remember that question I had about which of the 3 scales of map would be the most detailed? It was the one with the smallest number. That means it's zoomed in. The smaller the number, the 25,000 would have a more detailed look at a more specific area. The bigger the number, the broader the region you're looking at. Do you remember what kind of landform this was? If not, you need to go back and look. I bet you knew this one pretty easy. This was a mesa. The prior one was a hoodoo, or a whole bunch of hoodoos actually. Remember, mesas are flat on the top and very steep and broad. This is not a mesa. Can you identify what this is? This is a regional feature, much like a mesa, very flat, that got uplifted. And you are correct if you said plateaus. What kind of landform is this? Not a mesa, not a plateau, but has an irregular surface, much thinner and straight up and down sides. If you answered butte, you were correct. What kinds of mountains are these? Do you remember? These were the Grand Teton range. So I need you to go back and look at that and determine what kind of mountains these are, because they're going to be on your test. What kind of volcano is Mount St. Helens? That's what you're looking at here. Can you remember how it was made and why the front end of it's completely missing? That gives you a clue as to what type of volcano it is. So does all the snow-covered caps at the top. That's a good clue that you're looking at a special type of volcano. Can you remember what type of feature that Crater Lake is? Here is Wizard Island. My goal for you after you've gone through these lectures is to try to interpret landscapes with a completely different pair of eyes, seeing that there's a diverse history geologically, to understand how that earth feature or form was created. Because once you start doing that, then the world around you has different meaning, it has different significance, and you never look at the world the same way because you're seeing this ongoing history that's constantly in a state of change. I will see you at the next lecture. Bye.